Welcome back. In today's lesson, we will continue with our discussion into the topic of fractions, otherwise known as quotients. We will discuss the concept of identifying an improper versus a proper fraction. We will discuss the idea of fraction multiplication. And finally, we'll talk about fraction reduction so you guys can get to your homeworks. All right, so starting off the bat, improper versus a proper fraction. What does it mean? So in the last discussion, we introduced this idea that a fraction exists anytime you take one integer represented by this letter A and you divide it by another integer represented by the letter B. We call this a quotient. And the quotient has a couple of properties. One of the properties is that if you have a quotient and A is greater than or equal to B, then we call it an improper fraction. So what does it mean? It means, say my B was 2. Say my B was 2. If I have a value of A that is either 2 or greater, say 3, then I have an improper fraction. So this would be an improper fraction. Okay. If I had something like 7/3, the top number is greater than the bottom number. And so this is another improper fraction. Now, one of the reasons why it's called an improper fraction is because an improper fraction is any number which can divide and create some sort of a whole number quantity at the end of the day. Now, with many of these improper fractions, you're also going to get some sort of a trailing decimal in many instances. But if you took, say, the improper fraction 8/2, if you guys recall, this literally means 8 divided by 2, which we know must equal 4. So at the end of the day, after we do division, we know that this fraction isn't really a fraction at all, but rather it's equivalent to the number 4. Hence the reason why it's called an improper fraction, because we usually associate fractions with this idea that it's a quantity that's less than 1. But here you see that if you define a fraction as just taking one integer and dividing it by another integer, then in the loosest sense, if that integer happens to be greater than or equal to whatever the bottom number is, which we call the denominator, don't forget this bottom number, we call that the denominator. If the numerator is greater than or equal to the denominator, we will call that an improper fraction, because at the end of the day, the fraction itself will divide out and you'll have some sort of a whole component part of the fraction. And we'll talk about what to do with that whole component next week. But for now, we'll just introduce this idea that it is, in fact, an improper fraction. Okay. Note that I said greater than or equal to the denominator. So if you have a fraction like 8/8, because this will divide to be a whole number such as 1, this would also be an improper fraction. 7/7 would be an improper fraction. Okay? 6/6 would be an improper fraction, because these quantities are strictly, they're not really a partial quantity at all. They're not really a fractional quantity at all. They're actually equal to a whole number. Now, on the other end, or on the other side of things, if you have two integers, one integer divided by another integer, if your A value, the top number, the numerator, is strictly less than the denominator, which is represented by your B value, then you would say you have a proper fraction. Or just what we call a regular fraction, okay? So like 1/4, this would be a proper fraction. It is a special type of proper fraction in that it is, in fact, called an Egyptian fraction. owing to the fact that the Egyptians used these special types of fractions, such as 1/4, 1/3, 1/2, so on and so forth, in their construction calculations. So we call it an Egyptian fraction, but in particular, anytime the numerator is strictly less than the denominator, you'll just refer to that quantity as a proper fraction. Okay. And note that um, an Egyptian fraction is just a special type of proper fraction. Not all proper fractions are Egyptian fractions. The Egyptian fraction is specifically 1/3, 1/4, 1/2, 1/6, so on and so forth. So these would all be proper fractions, but they would also be what are known as Egyptian fractions. Okay. Now, at some point, we may think to ourselves, what happens if we try to take, I don't know, one fraction, such as 3/2, and maybe we try to multiply it with another fraction like 1/4. We ask ourselves, what is this equal to? This type of problem might come across at first as a little bit of a brain teaser, because if you guys recall the basic definition of multiplication, whenever you have one number multiplied with another number, this is literally read as a number, or not a number, but a sets of a sets of b. So if you have 3 times 2, you would say 3 sets of 2. Now, the problem is that when it comes to 3/2 times 1/4, this is literally saying 3/2 sets of 1 from 4. And of course, the question is, how are we supposed to interpret such a statement? Now, a piece of the clue as to how you're supposed to go about multiplying these improper fractions actually comes from the definition of composite numbers that we introduced in our last video. Consider the definition of a composite number. We said that whenever you take a unit fraction, such as 1/b, or a Egyptian fraction, such as 1/b, and you multiply it by a, or some number, so a just means some number, then what's going to happen is you get a over b, which is the typical way that we define a quotient. Okay, so, but how does that help us here? Well, if we think about it, what we're going to do is we're just going to try to pick a number a, pick a number b, and then what we'll do is we'll increment a and try to look for a pattern. So I'll pick an easy a, I'll pick 1, and maybe I'll pick an easy b value, I'll pick the value 5. Okay, so say I have 1 and my b is 5. So according to the definition of a composite fraction, anytime you have a times 1/b, in this instance, it would be a times 1/5. Well, what does that mean to us? Well, we would read this as one set of 1/5. And of course, that would just be one single 1/5. It would be like a fifth of a candy bar floating around in the ether somewhere, in space somewhere. If I now pick another number for a, maybe a somewhat larger number than 1, like 2, we might be able to establish some sort of a pattern here that emerges with the numbers. So I'm going to leave my b the same. I'll leave my b as 5. So we'll have 1/5 multiplied with 2, and we'll just see what happens. Well, if I say that I have 2 sets of 1/5, or 2 sets of 1/5, then it literally would mean that I've got 1/5 plus 1/5, because recall 2 sets of 3 would literally mean that you've got 3 plus 3. two sets of 4 would mean that you've got 4 plus 4. So I hope this is making sense to students. If I say that I've got two sets of 1/5, it literally means I've got 1/5 plus 1/5. Well, how many fifths do I have? I have 2/5. If I have three sets of 1/5, I would have 1/5 plus 1/5 plus 1/5. And how many fifths do I have? I have 1, 2, 3 fifths. If I had four sets of 1/5, I would have 1/5 plus 1/5 plus 1/5 plus 1/5. So I would just count up how many fifths I have. I have 1/5, 2/5, 3/5, 4/5, 4/5. Okay. So what seems to be happening here? Well, if we consider one fact that we may remember from grade school, recall that any number divided by 1 is just the original number. Do you guys remember this fact? 4 divided by 1 is always equal to 4. And we could always represent 4 divided by 1 as being a special fraction, 4/1. The same, of course, would be true for 3/1. 3/1 would equal 3, and we could represent the fraction 3/1 as 3 divided by 1. 2 divided by 1 would be 2, and I can represent this as 2/1, so on and so forth. What this means is that we can rewrite this 2 times 1/5. The 2 times 1/5 as 2/1 times 1/5. And we know that that is equal to 2/5. We can rewrite the 3 times 1/5 as 3/1 times 1/5. And we can write the 4 times 1/5 as 4/1 times 1/5, which gives us 4/5. Awesome. I hope you guys see the pattern. I hope you guys see the pattern that it appears that all we're doing when we multiply these fractions together is it's like we're multiplying the top with top numbers and the bottom number with bottom number in order to obtain whatever fraction we need. And in fact, that is the pattern. So fraction multiplication may be defined as follows. If you have one fraction, you multiply with another fraction, you are always going to multiply across the top and across the bottom. So suppose A over B represents my first fraction and C over D represents my second fraction. I don't know what A is. You don't know what A is. I don't know what B is. You don't know what B is. I don't know what C is. You don't know what C is. I don't know what D is. You don't know what D is. We don't have to know. These numbers could be like 10, 20, 5 billion, negative 5 billion. They could be whatever numbers we want them to be. But once we decided on the numbers that stand in for A, B, C, and D, our fractions will always multiply according to the following formula. We will always take the top numbers and multiply them with each other, and we will always take the bottom numbers and multiply them with each other. So to answer the question of how do we deal with 3/2 times 1/4, we would, of course, line our numbers up with the formula. And in this case, my A would be 3, my B would be 2, my C would be 1, and my D would be 4. And so using this little formula, we've got 3 times 1 over 2 times 4. 3 times 1 is 3, 2 times 4 is 8, and that is our answer. That's pretty much all there is to this. If you will have another example, suppose we have 5/2 times 7/3. 5 times 7 on top, and we would do 2 times 3 on bottom. 5 times 7 gives us 35. 2 times 3 would give us 6. So if we took 5/2 and multiplied it by 7/3, we would arrive at 35/6. Let's do another final example. Negative 4/6. 7 times 1 over 8. What would this equal to? Now, once you start introducing the negative signs into these fraction problems, you always have to slow down and just watch out for those negative symbols. But basically, the same process that we have above would apply here. We're going to take the top numbers, we're going to multiply them across the top, and we're going to take the bottom numbers, we'll multiply those across the bottom. So we have a negative and a positive. We know that's going to be a negative. We'll have 4 times 1 on top. We have 7 times 8 on bottom. Note, the 7 is a whole number and it's positive. The 8 is a whole number and it's positive. Yes, there's a negative value in the top, but we're going to associate that negative number only with the 4. Okay, so once I've dealt with the negative number on top, I don't have to worry about the negative. Don't let the negative symbol confuse you. Either pick the negative to be on top or on the bottom number. I usually pick it to be on the top number. We'll see that it doesn't really matter where the negative goes, and it can move around. Like I could have rewritten -4 over 7 as 4 divided by -7. These are equivalent fractions. Okay, even though I've changed where that negative symbol is in my fraction itself, they're actually equivalent fractions. And because of this, I really, really have to be careful with the negative symbol because it could get lost as I'm doing my mathematics. But on the other hand, I shouldn't necessarily let the negative symbol get confuse me because I can always just associate it with the top number or the bottom number, whatever seems to make the most sense to the student. For me, it's the top number, and you could just multiply across. So I took the top number, which happened to be -4 in this case. We did a negative and positive, and then I wrote down the negative symbol that you see. At that point, I'm going to record 4 times 1. Yes, we can do it in our heads. Write it down on paper. You never know when a simple calculation like that is going to kill you as we go on in this class. Now we'll do 7 times 8, which should give me 56. And that would be our answer. Of course, at this point, we need to ask ourselves, is this the best answer? Now, students who are at this level, they may be used to just providing an answer, and if it's sufficient, they think it's okay to move on. But suppose we were in construction, right? We might actually need to measure out 4/56 of a foot or 4/56 of an inch in order to perform some sort of a calculation or in order to cut whatever parts we might be working with to size in order to build the part we need to build or the assembly we need to assemble. And of course, 4/56 is this kind of weird fraction. It would be difficult to like take a rope, cut it into 56 individual pieces, and then take 4 of those pieces, okay, of a specific size. That would be the first challenge. But then the second challenge is maybe we don't need to cut it into 56 little parts. It turns out that there might be a more simplified, what's called a simplified form of this fraction, which is equivalent to -4/56 in this instance. And if that was the case, which it is, that might facilitate us actually being able to do some useful work in the real world. Because all of these calculations, especially with fractions, are calculations that people actually have to do on the job site in the real world, especially if you're in manufacturing, in the metal manufacturing or the metal trades. You're going to be using fractions all the time for different things. If you're like a CNC machinist or a welder, you're going to see these fraction calculations all the time. So you really, really need to be familiar with how you handle these quantities, okay? But then you also need to know once you get an answer that you want an answer that's actually practical for the problem that you're trying to solve. So if you're trying to measure something with a foot, you know, the foot yard or the yardstick, okay? Now, if you were measuring something with a foot, you need that answer, whatever your answer is, to be in inches or something that's close to an inch. And of course, a foot is divided into 12 inches, right? So 4/56, something that's divided into 56 parts, that's not going to be the most helpful type of measurement to measure using a yardstick or to using a ruler, a standard foot-long ruler. Okay. So let's talk about the problem of equivalency classes, otherwise known as equivalent fractions. So consider the following. Consider taking a candy bar and slicing the candy bar in half. If you slice the candy bar in half, you would, of course, tell yourself that you have 1/2 of a candy bar, which is all well and good. But here's the thing. Suppose you took that candy bar and instead of slicing it into 2 equal parts, you instead made 3 cuts into the candy bar and took 2 of the pieces of the candy bar. And I know that I drew my picture. It's not exactly lined up here, but if you can use your imagination, it sure looks like these 2 pieces of a candy bar sliced 4 ways is equal to 1/2. And then if you took your candy bar and instead of slicing it into 4 equal pieces, you instead did this number. Okay, my pieces are not the greatest. Try that again. Let's do 1, 2, 3. 1. Okay, that's pretty good. If you took 3 pieces from 6, you'd see you'd have pretty much the same amount of candy bar as 2 pieces from 4. So what is this picture? What does this diagram tell us? This diagram tells us that 1/2 of a candy bar is the same amount of candy bar as 2/4 of a candy bar, which is the same amount of candy bar as 3/6 of a candy bar. And it turns out that 3/6 of a candy bar would be the same as 4/8 of a candy bar, which is the same as 6/12 of a candy bar, which is the same as 7/14 of a candy bar, so on and so forth, all the way to the end of time. And it turns out that I could sit here until the universe died and keep naming off new fractions that would be equal to 1/2 of a candy bar. And what's really interesting is that for every single quotient, for every single fraction that exists that I could possibly imagine, there exists an infinite number of equivalent fractions that are in fact the same quantity as an initial or more simplified fraction. We would say that 1/2 is a simplified fraction because it's the most simplest way that I could have taken a candy bar and cut it such that you get exactly 1/2 of the candy bar. Yes, we could have taken a candy bar, slice it into 14 pieces, and take 7 of those pieces. And you would have functionally 1/2 of the candy bar at your disposal. But slicing it into 14 little tiny slices is rather tricky to do. So here's the thing. In the real world, you're usually left after performing one of these mechanical calculations with something that looks like 4/56. And what you're going to try to do is you're going to try to figure out, hey, what is this equivalent to in a simplified form, so that instead of having to take a foot long ruler or a yardstick or whatever measuring device you have at your disposal and cutting it 56 ways, we can instead cut it the least amount of times, or maybe the measurement is even on the measuring device itself, and so you can just quickly identify it. Like 1/2 of a foot is a measurement that's very easy to identify for anyone to identify, but especially a worker who's in a factory style environment. So it would be better to have that as an answer. Okay, but how is this done? Well, we are going to introduce this idea that there are 2 different methods by which you can simplify a fraction. On the one hand, we can use what is known as prime factorization to simplify a fraction. Taking the example of 7, sorry, not 7/14. We'll take the example of 4/8. 4 over 8, if we look at the prime factors of 4, the prime factors of 4 happen to be 2 times 2. And so the way in which you're going to simplify a fraction using the prime factorization method is we are going to take the top number, take the numerator, the number in the numerator, and we are going to write out all of its prime factors. And then we will do the same thing for whatever number is in the bottom of our fraction or whatever number is in the denominator of our fraction. So since I have 8, 8 is the same thing as 4 times 2. And of course, 4 is the same thing as 2 times 2. So 2 times 2 times 2 gives you 8. Now, what we're going to do here is we will give ourselves, we'll insert an imaginary 1 for this specific case. It doesn't really matter. 1 times anything is just that something. So 1 times 2 just gives you 2. We didn't change anything. What that's going to allow us to do is to see the following. If we were to cross out the numbers on top and on bottom that are sets of each other. So I have a set of 2's here, and I have a set of 2's here. If I was to cross out the prime factors that have sets, and I examine what's left over, which happens to be this 1/2, you'll see that I can arrive at the initial quantity, 1/2, the simplified fraction, by merely finding the prime factorization of the top number and the bottom number, and then crossing out terms that are in common. But is that legitimate? Okay, here's the big question that students should always ask themselves. Whenever a mathematician throws up some sort of new procedure or new process on the board, students should always be asking themselves, is this procedure legitimate? Is this procedure algebraic? And if so, why is this legitimate? How is it legitimate? Well, what's happening here when we quote unquote cross out terms on the top and the bottom of our fraction is that we're not really like annihilating those terms. They're not disappearing magically. Okay, we had this fraction 2 times 2 times 1 on top and 2 times 2 times 2 on bottom. And what this fraction stands for is it actually stands for 3 individual fractions that are all being multiplied together, because a fraction multiplies across the top and across the bottom. And so if we've defined fraction multiplication as the following, where you've got one fraction times another fraction, and all that means for you to do is multiply across the top and the bottom, what we do with prime factorization is we're essentially going backwards. We take a number, we find out what the A and C terms are, i.e., what the prime factors are for the top number, and then we find out what the B and D term happens to be, i.e., what the prime factorization is for the bottom number, and then we go backwards. We decompose it into a series of fractions. And then what that's going to do for us is 2 divided by 2, this term here, 2 divided by 2, well, that's just 1. And then you have 2 divided by 2 here, which again is just 1. And finally, you're left with 1/2. So 1 times 1 is 1 times 1/2 gives you 1/2. And of course, usually with these prime factorization problems, we're going to skip all of this stuff. You can definitely use it. Don't get me wrong. You can definitely use this method just to check your work. But ultimately, we're going to use this crossing out notation to represent this idea that you can decompose your fraction into a sequence of fractions that are all multiplied together. And all we're doing is we're crossing out terms that are in common. Okay, let's see another example. So suppose you have, I don't know, 52 over 104. Okay. And you're like, what is this equal to? And in fact, I think maybe it's also, it may also be 1/2. So let me check. Let me try a different number. Let's do 70. I want to pick a good number. 74. Okay. 74 over 104. So the way that I would find the prime factorization of any number, whether it be the number that in the numerator, i.e. the top of our fraction, or the number in the denominator, the bottom of our fraction, is I would check to see if those numbers themselves were even. And then if they're even, what I'm going to do is I'm going to divide them by 2. And I'll just keep repeatedly dividing this number by 2 until I get nothing left. And so, or the only terms I have left over are prime. So as an example, I'll take 2. I know that 74 is even, so we'll divide 2 into 74. 2 into 7 goes 3 times. 3 times 2 is 6. Subtract. 7 minus 6 is 1. Drop your 4. 2 into 14 goes 7 times. 7 times 2 is 14. Subtract. You get 0. So we found that 74 is the same thing as 2 times 37. Now, we're going to do the same thing for the bottom number. 2 will go into 104. 2 goes into 10 5 times. 5 times 2 is 10. Subtract, you get 0. Drop your 4 down. 2 into 4 goes 2 times. This is 252. I think 37 is prime. I'm pretty sure it is. I know that 3 times 13 gives you 39. But 9 times 3 is 27. 9 times 4 is 36. 17 times 2 would be 34. So yeah, I don't think that there's any number. I think 37 itself is prime. And I'm going to stick with that answer. So basically we're stuck here. I've got 2 times 37, and while I have not necessarily found my prime factorization for 52, and I could keep going if I wanted to with breaking it down, what's going to happen is, because I only have 2 prime numbers on top, and I have a set of 2s that I can see with my eyes, we can go ahead and we'll cross out the set of 2s that we have on top and on bottom, and that will, in fact, just leave us with the reduced fraction 37 over 52. So this was kind of a special case. And of course, it's because I'm picking numbers more or less at random, whatever suits my fancy. So I just happened to pick 74. So when it decomposed, it just had, 2 prime numbers, 2 and 37. So that's a little bit of a weird case. But usually we would keep going on the top and the bottom until you get a sequence of prime factors, more or less like what we got up here. So let's try another one. Do 54 over 82. Okay. So here again, 54 is prime number. So I'll go ahead and divide 2 into 54. 2 into 5 goes 2 times. 2 times 2 is 4. Subtract 5 minus 4 is 1. Drop your 4. 2 into 14 goes 7 times. 7 times 2 is 14. Subtract gets you 0. So you would have 2 times 27 on top. Now, 27 is not a prime number. It's the same thing as 9 times 3. And 9 is not a prime number. That is the same thing as 3 times 3. So you'd have 3 times 3 times 3 times 2 on top. And on the bottom, in your denominator, you'll have 2 into 82. Well, that should go 41 times. So we'll have 2 and 41. And unfortunately, I do believe that 41 is a prime number, although we could check this. We'll go ahead and I'll take a second just to check. It is in fact prime. So at this step, you could have stopped if you wanted to, because there's no new information that you would be able to find, given that 41 is prime, 2 is prime. And although 27 can be decomposed into these primes, 2, 3, 3, and 3, it wouldn't necessarily give you any new information, because what's going to happen is you would have 2 and 41 in your denominator. So yeah, you could eliminate the 2s, a set of 2s, one from the numerator, one from the denominator, and you would be left with 3 times 3 times 3, or 27 on top, all over 41. So that's not necessarily any better than if you had just stopped at this step right here, the second step, and just crossed out the 2s in the first place. Just look for that as you're going through this problem statement. Look for these different ways to approach solving or finding a solution. All right, let's try 165 all over 355. Now, students should know that if a number ends in a 5 or a 0, that number will be divisible by 5. And so in this instance, we definitely have 355 on the bottom. That's divisible by 5. Let's go ahead and go to the side somewhere. We'll divide 5 into 355. 5 goes into 35 7 times. 7 times 5 gives you 35. Subtract, get 0, drop your 5 down. 5 goes into 5 1 times. Man, why do I keep getting all of these prime numbers today? Today, I am picking all of the prime numbers in the book. 41, 71, 37. My goodness. I have never had this this much luck picking prime numbers in my life. I'll tell you guys. Okay. Let's try the top number. So we'll do 5 into 165. So 5 goes into 16 3 times. 3 times 5 gives you 15. Subtract 16 minus 15 gives you 1. Drop the 5. 5 into 15 goes 3 times. She'll have 5 and 33. I will go ahead and check to see that 71 is prime. I believe it's prime. It is, in fact, prime. Okay. So we'll stop at this step. We'll go ahead and we will divide out our 5, and that will give us 33 over 71. And this is our simplest fraction. Now, not necessarily the most useful fraction, but the simplest fraction. Okay, it would still be rather challenging to take 33 parts from a quantity that has been sliced 71 times. But can it be done? Of course it can be done. Now, there are other methods for performing fraction simplification, and one is called the GCF. Fraction simplification method. So if you have a number such as 124, and maybe you've got another number 244, and you want to simplify this particular quantity, it turns out that instead of finding, say, the prime factorization and just crossing out the prime factors that are in common on the top and the bottom, you could instead find the greatest common factor of both the numerator and the denominator, and then you divide the numerator and denominator by that number. So how we're going to do this, though, is rather similar to the prime factorization method. I always find my GCF by just finding my prime factors anyways. So this technique does add an extra step of having to find the prime factors. 2 will go into 124. We'll go to the side of our page. 2 goes into 12 6 times. 6 times 2 gives you 12. Subtract. Drop your 4 down. 2 into 4 goes 2 times. So you'd find that 124 is the same thing as 2 and 62. 2 should go into 62 31 times, I believe. And of course, 31 we found out before was a prime number, so we should stop there. Now for 244, by contrast, let's go ahead and find its prime factors. 2 goes into 24 12 times. 12 times 2 gives you 24. Subtract, you get 0. Drop your 4 down. 2 goes into 4 2 times, so you get 2 and 122. And of course, now 11 divides 121, but 122 is not divisible by 11, unfortunately. So we can go ahead and divide it by 2. 2 goes into 12 6 times. 6 times 2 is 12. Drop your 2 down. 2 goes into 2 1 time, so you have 2 times 2 times 61. And I believe 61 is also going to be prime. So look at that. Now, how the GCF technique works, if you guys recall from the previous lesson, is that you're going to cross out terms that are in common between the top number that you found a prime factorization for and the bottom number that you found a prime factorization for, and you simply write it once in your GCF column. So since I have a set of 2's that are in common between 124 and 244, for my prime factors, I will write a 2 once underneath the GCF column. And then I have another set of 2's. So I will write another 2 next to my 2. Now what we do is we take 2 times 2 in this case. We multiply the numbers that we uh, crossed out, if you will, with each other. So I had one set of 2's, 2 sets of 2's. So we, for each set, wrote 1, 2 once. And then we take all of the numbers that we had obtained from crossing out a number on the top and the bottom. We multiply those together, and in this instance, we have 2 times 2 is equal to 4, which would be our GCF of 124 and 244. Now, what does this tell us? This says that if I took the top number, 124, I divided 4 into it. Well, 4 goes into 12 3 times. 3 times 12 is, sorry, 3 times 4 is 12. You get a 0 remainder, and 4 goes into 4 one time. And of course, we would back multiply and we would get a 0 remainder. So this is saying that 4 goes into 124 exactly 31 times. If we took 4, though, and we divided it into the bottom number, 244, 4 should also go into our bottom number pretty easily. 4 is going to go into 24 6 times. 6, 12, 18, 24, right? 6 times 4 is 24. Subtract, you're going to get 0. Drop your 4 down. 4 into 4 goes one time. 1 times 4 is 4. Subtract, you get 0 remainder. And so 4 goes exactly 61 times into 244. Using the GCF method, what this tells you is your fraction, the numerator of your fraction should be 31, and the denominator of your fraction should be 61. And that would be your answer. Now, of course, this method is not more efficient than what we were doing before. And in fact, what we were doing before, in my humble opinion, is actually a shortcut to the GCF technique. However, what you should know is that there are other methods of finding a GCF, some of which are faster than this method. Finding the prime factorization is not necessarily in the real world that efficient. It turns out that computers are rather bad at division. And so if you had a really, really, really large number and you were to try to find the prime factors of this really, really large number, like say a number that's, bigger than 10 raised to the 12. So a number 1 with 12 zeros, 12 trailing zeros. So a really, really massive number, bigger than 100 billion. Okay. If you had such a number, it would be very difficult for your computer to actually find all of the prime factors. And in fact, there are numbers that are so big that it would be virtually impossible for your computer to find all the prime factors before the universe died. Okay. So what this means is that there have had to be other methods for finding, say, the GCF of really, really large numbers, especially for computer science applications. And as a result, there are methods that are pretty efficient for finding a GCF, but there are not necessarily methods that are as efficient for finding all of the prime factors of a given number. And what that means to you is it's much easier in reality for a computer to go from, say, 124 over 244 straight to 31 over 61 than it would be for a human to do that, because to us, it would make more sense because of where we're coming from to just find the prime factorization of a number. Of course, that's not necessarily as computationally efficient as, say, just finding the GCF. In this instance, we had to do the prime factorization to find the GCF, but it's not always necessary to do that. At any rate, that is all we have for fraction simplification. Uh, I'm not going to use the GCF method to simplify my fractions. I'm just letting students be aware that there is such a method. And when you see it on your homework, just refer back to this section as to how you can use it to your advantage. I will always pick the prime factorization method because it just makes more sense to me. There is one last rule of fractions that we need to learn, and that is fraction division, i.e., what happens if you have one fraction and you divide it by another fraction. If you have one fraction, such as a over b, and we divide it by another fraction, like c over d, all that you have to do is you flip the second fraction and you multiply. This flip fraction is what is known as a reciprocal. And it turns out that what's going on when you actually perform division of any kind is that you're multiplying by what is known as a reciprocal. And as a result, when you when you divide by a fraction term, it's the same thing as simply multiplying by the reciprocal of that fraction. Okay, it's just kind of a definition there. We won't necessarily prove that in this class at this moment in time, but as we go along, we might come back to this subject and just prove that this is in fact the case. For now, it's sufficient for students to just memorize that what happens when you take one fraction and divide it by another is that all we're going to do is we're going to flip the bottom fraction and multiply. So what does it mean? It means if I wanted to take 3/4 and divide it by 2 over 7, all we're going to do is we're going to leave the first fraction where it is. The 3/4 stays 3/4, but you're going to multiply by the second fraction that has been flipped. Okay, so instead of 2 over 7, you're going to multiply by 7 over 2. 7 times 3 will, of course, give us 21, and 4 times 2 will give us 8. So at the end of the day, we will get 21 over 8, and that is our answer. Another example, if you have negative 3/5 and divided it by 2 over, well, I don't want to do 2. Keep using the same numbers over and over again. We'll do 8 over 8 over 11. All you're going to do is you're going to leave your first fraction the same. You will flip the bottom fraction just like so. Negative to positive is a negative. You'll do 3 times 11 on top, and you'll have 7 times 8 on bottom. 3 times 11 gives you 33. 7 times 8 gives you 56, and that is our answer. When you get to this step, you have to always be aware that you might have to simplify the fraction. In this instance, though, 33's prime factors are 3 and 11. 56 prime factors are 7 and 2, okay? So since 2 isn't divisible into 3, 7 isn't divisible into 3, 2 isn't divisible into 11, 7 isn't divisible into 11. Negative 33 over 56 is going to be the simplest form of that fraction. It doesn't look nice. It's definitely not pretty, but it is the simplest form of that particular fraction. That's all I've got for you guys today. I'll see you in the next lesson.